Find the equation of the tangent line for x cubed equals y cubed equals to plus y cubed equals 6x cubed at the point 3, 3. And of course you might want to verify that that point is on the graph of that function. Well, so what's this 3 cubed? So that's plus 3 cubed, 6 times 3 times 3. Well, so that's 9 plus 9, that's 18, or actually no, that's 3 cubed, which is 27, and plus 27, that's a 54, and this is 3 times 3, which is 9, 6 times 9, that's a 54 also. So indeed, this point is on the graph of the given function. Well, it's not a function of the given equation. So let's go about the implicit differentiation part. So number 1, x cubed plus y cubed equals 6xy. Alright? So let's see. So let's find the derivative of x cubed. And what's the derivative of x cubed? 3x squared. What's the derivative of 3y cubed? 3y cubed, 3y squared rather, but because we're differentiating a y, essentially we're using the chain rule to differentiate this with respect x. So on the right hand side, let's differentiate this product. However, I'm going to have the 6 outside and then do the product between x and y. So again, to recall the product rule for differentiation, let me write it down here. That's u prime, the derivative of a product u prime v plus v prime u. Alright, so that is, in this case, okay, the derivative of x, which is 1, times the derivative times y simply, plus the derivative of v, which is y. The derivative of y is 1 times simply dy dx times the quantity u, which in this case is x. So we're done with the calculus part of the problem actually. Let's use algebra to solve this equation for dy dx. That's going to give us the derivative. So 3x squared plus 3y squared dy dx equals 6y plus 6x dy dx. So number 1, let's get all the terms containing dy dx on the left hand side of the equation. So 3x squared plus 3y squared dy dx. I'm going to move this term to the left hand side as negative 6x dy dx, and that should be equal to 6y on the right hand side. Now let's move all the terms that do not contain dy dx to the right hand side. In this case, all the one-to-one term we need to move is the 3x squared. So this will be 6y minus 3x squared, and over here notice how we have a factor of dy dx. At the same time, I'm going to do that factoring, and so that's going to be dy dx times 3y squared minus 6x. And we're only one step away to get the dy dx by just dividing both sides by 3y squared minus 6. So this is dy dx equals 6y minus 3x squared over 3y squared minus 6x. So number 1, that's the derivative. So in this case, they're asking us to find the equation of the tangent line. So to find the equation of a line, we need 2 pieces of information. What are those pieces of information? The slope and what else? And a point, right? The slope and a point. So we have a point, 3, 3. All we need is the slope. How do we get the slope? From the derivative. But in this case, notice how the derivative is, it's 2 variable. It's defined by 2 variables. So dy dx will be evaluated at, this bar means evaluated at the point 3, 3. So wherever we see the letter x, we're going to plug in a 3. Wherever we see the letter y, we're going to plug in a 3 as well. So 6y, so which is 3 on all cases, minus 3 times 3 squared divided by 3y, which is 3 squared, minus 6 times 3. So, okay, so 6 times 3, that's 18. Minus 3 squared, which is 9 times 3, that's minus 27. Over, again, another 27, minus 18. Alright, so 27 minus 18, isn't that a 9? So 9 over, actually negative 9 over 9, which equals negative 1. Alright, so that's our slope for that equation at the point 3, 3. So we have all the information that we need to get the equation of the tangent line at that given point. When we can simply use, again, y minus y1 equals m times x minus x1, where this is the m, the slope. So from here it's all plugging in numbers. Y minus y1, y minus 3 equals to m, which is negative 1 times x minus also 3. For this equation, yes, we can solve for y. That's y minus 3 equals negative x. Careful here, negative times a negative, that should become a plus 3. And adding 3 to both sides, y equals to negative x plus 6. So that's the equation of our tangent line. So basically we're doing the typical whole problem, not just finding a derivative, but applying that derivative to find the equation of a tangent line at a particular given point. Alright, so let's look at another example. And for the next example, they're only asking us to find dy dx, the derivative. And again, in this one, trigonometric functions are going to be involved. So let's see how this is going to work like. Alright, so what do we have? 2xy cubed. So that's a product. Let's use the product rule again. Let me write that product rule again. So that's u v prime. That's u prime v plus v prime u. So that's going to be, okay, so whenever you have a product with a constant multiplying outside, leave the constant outside and focus on the product as xy cubed. Alright, so the derivative of u, which in this case is x, the derivative of x, which is 1, times v, which is y prime, y cubed rather, and plus the derivative of y cubed, which is, what's the derivative of y cubed? 3y squared dy dx. So that's the derivative of the product, right? Oh, don't forget the u part, which is x. And then, so that's the derivative of the product. What's the derivative of y cubed, of y squared rather? This one right here. Isn't it to y dy dx?
Okay, I don't know if you already explained this, but why are you putting the derivative of y?
Yeah, we went over that last time. So how we connect the chain rule, because in this case we're differentiating everything with respect to x. So in this case, this y function is a function y that depends on x. So we're basically differentiating this y with respect to x using chain rule. All right. So now let's differentiate the cosine function on the right hand side. So what's the derivative of cosine? Negative sine of x plus y, but in this case we need a mini chain rule to differentiate x plus y. So what's the derivative of x plus y? 1 dy dx. Alright. So okay, so oh my god, let's simplify this madness. This will be 2y cubed plus 2 times 3, which is 6y squared, or xy squared dy dx. And well, so that's 6x y cubed or y squared dy dx, and plus 2y dy dx. And over here, well, I would have to distribute the negative sign times 1 and times the dy dx. So that's going to give us the following. That's going to give us simply negative sine x plus y minus sine of x plus y times 1, that times simply dy dx. And again, just like the previous example, let's have all the terms containing the dy dx on the right hand side, and all the terms that don't have a dy dx, have them on the right hand side. I'm going to do both movements in one shot. So this 2y cubed, I'm going to move it to the right hand side with opposite sign, and this negative sine x plus y dy dx, I'm going to move it to the left hand side with the opposite sign negative as a positive. So this will be number 1, 6x plus y, 6x y squared dy dx plus 2y dy dx plus sine x plus y dy dx, and equal to negative sine x plus y and minus 2y cubed. So the idea of having all the terms that contain a dy dx on the left hand side is so we can make it a common factor and then just divide out what we are left when doing the factoring. So in this case, dy dx equals, times 6xy squared plus 2y plus sine x plus y equals to negative sine x plus y minus 2y cubed. And well, to get dy dx by itself, just divide by this whole madness we have in here. So that's going to be dy dx equals, actually we can factor out this negative and have all these two terms positive, sine x plus y plus 2y cubed divided by 6xy squared plus 2y plus sine x plus y. Final answer. In summary, what are we doing? Well, we are putting all these differentiating rules together. However, from the point of view of an equation, but the thing is that all the terms that contain the dy dx, have them to the left hand side to make it a common factor, and only then divide out by all the factors that we get so we can get the derivative in this question.
Will problems as complexity be on the exam?
Excuse me?
Will problems as complex as this one be on the exam?
Possibly something like this involving a product and a trigonometric or an exponential, maybe, something like e to the x squared plus y squared or e to the xy, something like that. Question?
Did you background the 2 in the very beginning? That was the 2 outside the parentheses?
So I left it outside to just focus on the product rule, and then I distributed the end result. So 2 times 1, that's 2, and 2 times 3, that's a 6.
And then where did the plus 2y dy?
Plus 2y dy dx, it was left here.
Like on the very first line.
Oh, this one?
Yeah.
The derivative of y squared is 2y dy dx. Doing implicit. My pleasure. All right, let's see what's next in here. Do we have another example? Okay, the derivatives of inverse trigonometric functions. So we are going to find the derivative not of sine, cosine, but rather their inverses. Well, in this case, it turns out that we need implicit differentiation to get one of these or actually all of these derivatives. So actually, I have a summary in the definition box at the bottom of the page with all the differentiation formulas. So what I'm going to do is derive the first one or prove the first one using implicit differentiation and some techniques that you learned back in pre-calculus. So let's see. So number one, well, I want to find the derivative of arcsine, of the inverse sine function. Well, a common mistake is to say y prime equals cosine inverse of x. Well, that's because the derivative of sine equals cosine, but no, it's not the case. It's not going to be like this. So let's see. In this case, we need to write this as an implicit function. So if we have y equals, I'm going to leave a space here, sine inverse of x, I'm going to solve for x by doing the inverse of the inverse sine. And the inverse of the inverse sine is to take sine. Alright? This means we can cancel out sine with sine inverse because these are inverses or inverse functions to one another, just the same way e to the ln or ln of e. In this case, sine of inverse sine cancel each other. And we will be left with sine y equals to x. Alright, so what about this, this sine y equals to x? Let's think of this x as x over 1. But why? Because, well, I mean, can we just differentiate x? That'll be 1. Yes, that is true. However, we will construct a right triangle using this statement right here. So let's construct that right triangle. That right triangle, this is the angle. In this case, usually we use the letter theta, but this time I'm going to use the angle y because that's the dummy variable in this case for the sine function. And well, what's SOHCAHTOA for sine in this case? What's the numerator? Opposite over hypotenuse, right? That means opposite, which is x, and hypotenuse, which is 1. If we do the Pythagorean Theorem we're using these two pieces of information, so that's c squared equals a squared plus b squared. That's 1 squared equals x squared plus b squared. That means b squared equals 1 minus x squared, and b will be the square root of 1 minus x squared. So that's going to be this quantity. Alright? So, so let's see. Let's how about we take the derivative implicitly. Well, what's the derivative of sine? Cosine, isn't it? Cosine y, but because we're differentiating a y quantity, what do we need to multiply by? So is the derivative of sine y with respect x just cosine y?
Which you multiply by dy.
By dy dx, right? So by dy dx. And what's the derivative of x? Just 1. Alright, let's solve for dy dx. We get that by dividing both sides by cosine. Dy dx equals, that's 1 over cosine. But using trigonometric identities, what's 1 over cosine? Which one? Secant, right? Secant. So dy dx equals secant, but this is a secant of y, which is weird because I'm trying to find a derivative for the inverse sine in terms of x. We still have terms of y. We need to get rid of terms of y to turn them back into terms of x. So secant in this case. What's SOHCAHTOA for secant? What is that? SOHCAHTOA for secant? Hypotenuse over adjacent. So what's our hypotenuse here? Isn't that a 1? What's the adjacent? Isn't it this formula? Well, that second formula might look different because this is the derivative of the inverse sine function whenever we have a composite function, whenever the argument u is something other than simply x, which of course we will do something like that, and then we just multiply that by that derivative of that quantity inside parentheses. But in general, if it's just x, well, that's no need to multiply that, all right? And that's how we get the derivative of inverse sine using some pre-calculus techniques, as well putting it together with implicit differentiation. No, we don't have to derive this formula, so just one example is fine. So let's do some example. Let's find the derivative of y equals to inverse sine of the square root of x. Alright, so it would be a good idea to first rewrite this function as a sine inverse of x to the 1/2. This way, so we can use the chain rule property, or rather, so we can differentiate the root of x. We can now differentiate the root of x just the way it is. We need to write this in rational exponent form first. So, y prime. So the derivative of inverse sine is going to be 1 over the square root of 1 minus u squared. In this case, our u will be the quantity inside of the parentheses of the inverse sine function, which in this case is x to the 1/2. So that's square root of 1 plus x to the 1/2 quantity squared, but in this case times the derivative with respect x of the quantity x to the 1/2. So let me do one thing at a time. Right? Question. Yeah, thank you. That I messed up the sign here. So minus, all right? So, well, let's simplify this a little bit. So notice this squared times 1/2 reduces to simply 1. So that reduces to 1. 1 minus x to the first power. I don't need to write that first power. And then we need to differentiate this x to the 1/2. What's the derivative of x to the 1/2? So 1/2 x to the, subtract 1 to the exponent, what is that? Negative 1/2. And we're essentially done with the calculus part. The remaining part of the problem is just rewrite this in a nicer way. Notice this denominator too, I'm going to write it in front of the x. And so y prime equals to 2 root of 1 minus x. And this x to the negative 1/2, I'm going to send it to the denominator as x to the 1/2. And at the same time, I'm going to rewrite this x to the 1/2 as 2 root of 1 minus x times root of x. And we can leave it like this. Of course, we could combine this into a single radical. Well, how about we do that? That's fine. And that goes by the following property. Whenever you have the product of two radicals, that's the radical of a product. That's essentially the product rule for radicals. So let's put this together. That's 1 over 2 root of x times 1 minus x, which reduces to 1 over 2 root of x minus x squared. All right. So I think this will be a good result. Let's have a look at another example, and notice the notation in this case. We can either use the -1, which that's to indicate inverse function, or we can use the arc notation. Either way, you should see it either way, whether on the homework on WebAssign or on quizzes and exams.
Oh, by the way, talking about WebAssign, candidates on homework are still not uploaded.
Don't worry, it takes some time to let me pause this. All right, let's look at y equals 3x squared times arctangent of x over 7. Number one, what differentiation rules do you think we should use here? Product rule would be 1, and the other one is for the derivative of arctangent. Well, let me write them both. That's the derivative uv prime u prime v plus v prime u. And we also need the derivative of arctangent, which in this case the derivative with respect x of arctan of u, that's 1 over 1 plus u squared times du dx, right? So those are the two rules that we're going to use to differentiate this function. All right, u prime v plus v prime u, the derivative of u, which is 3x to the 4th power, what's its derivative? 12x cubed times simply arctangent x over 7 plus the derivative of arctangent. Well, be careful with this one. That's number 1. 1 over 1 plus u. 1 over 1 plus, but what's u in this case? X over 7. Alright, that's x, the quantity x over 7, quantity squared. But in this case, a mini chain rule suggests that we need to differentiate this x to the 7. And by the way, what's the derivative of x to the 7? That's 1 over 7. Alright? So 1 over 7. And well, let's see. So that's only v prime. We need to multiply that by u. So we're done with the calculus over here. Let's simplify, especially more about the second term. So number 1, I'm going to have this 3x to the 4th power in the numerator, and this 7 in the denominator. I'm just going to multiply across. How is that going to work? Okay, you'll see. So this is simply 12x cubed arctangent x over 7 plus 3x to the 4th power, and that's 7. This 7 right here is this 7 in the denominator multiplying 1 plus x squared over 49. Be careful because this power 2 will affect both the x in the numerator and the 7 in the denominator, and that's by the laws of exponents. Let me recall you that law of exponent. It's whenever you have a over b to the n power, that's a to the n over b to the n. That's the law of exponents that we're applying here. Alright, so we still need to simplify this second term because it contains a complex fraction. That means it contains a fraction inside a big fraction. So number 1, I'm going to distribute the 7, and so this will be 12x cubed arctan x over 7, and that's going to be plus 3x to the 4th over 7 plus, okay, what's 7 over 49? Doesn't that reduce to 7? X squared over 7. But still, this is a complex fraction. So what I'm going to do is multiply numerator and denominator by a global LCD. In other words, I'm going to multiply by the quantity that divides out the 7. In this case is 7. Multiply by 7, divide by 7. So 3 times 7, that's 21, x to the 4th, and 7 times 7, that's 49, and 7 divided by 7, that's simply x squared. Oh, hold on. Let me write it down. 12x cubed arctan of x over 7.
What is this arctan?
The inverse tangent function. Plus, and that's final answer. Coming back to your question, let me go back to the definition box. So for example, this sine to the -1 is the same as saying arc sine, arc cosine, etc. We can use the arc prefix or the -1 symbol. Either notation is fine.
Will we see arctan on the exam, or is it
Either one, so
we just need to know what it is?
exactly.
Where does the 1/7 come from on the first one?
Oh yes, because this x over 7 right here is the same as saying 1/7 of x, and the derivative of 1/7 of x is 1/7. All right. Yes.
So you use the chain rule?
Yes, it's a mini chain rule essentially. So it's because it's a arctan of some u, even though it's not, it's still a composite function. It's not a very complicated function. But what makes it tricky is this x over 7. Maybe write it as 1/7 of x, and it's easily to it's a lot more easy to see the derivative of the 1/7. Yes.
So you use the combination of the product rule and
Chain rule and arctan rule and general power rule. Yes, all those in the same problem. Well, this is the end of this section. Let's get started with derivatives of logarithmic functions. All right. So far we have found a derivative for an exponential function base e, even though I didn't give you the result of differentiating an exponential function with a base other than e. Well, it's going to be somehow involved. However, we still need to recall a couple of properties from exponentials and logarithms in order to find the derivative of logarithm base b of x. Well, so these properties that I'm talking about are the inverse properties between ln and e. All right, so let me list those properties. So on the one hand, we know that ln of e to the x equals x because ln and e cancel each other. They're inverses of one another. That's one property. The other one property is e to the ln of x equals to x as well. So number one, we use these properties primarily to solve logarithmic and exponential equations as another tool in an effort to get rid of the exponential or to get rid of a logarithm. However, we can use these properties to write exponential functions of some base that are not the natural e, the natural exponential, and turn them into an exponential. So, for example, what if we want to find the derivative of log base b of x? Well, number one, if we use the limit definition, we're just going to get stuck when we do, okay, so log base b, x plus h minus log base b of x. Good luck with this. Unfortunately, we don't have the necessary tools to go about this limit. So we're going to use, again, the inverse properties between logarithms and exponentials. And also we're going to rely on implicit differentiation again. So one thing to recall is that logarithm base b of x is the same as b to the y equals x. For example, what is this trying to tell us? For example, log of 25 on the base 5 equals to 2. That's because 5 to the second equals to 25. In the same way that log of 1,000 base 10, well, we don't need to write the base 10 in this case because a logarithm without a subscript in the g is supposed to be understood that the base is 10. And in this case, the logarithm of 1,000 on a base 10 is supposed to be a 3. That's because 10 to the third power equals 1,000. That's like writing back and forth between logarithmic form and exponential form. Alright? Well, so in general, logarithm of base b of x is the same as b to the y equals to x. So we're going to use this, we're going to differentiate this implicitly to obtain a formula to differentiate the natural log function. And well, I mean, the formula to differentiate ln is just 1 over x. I know it's really simple, but where is this coming from? That's the interesting part. So let's take the derivative of this function. All right, so okay, we can differentiate the function e to the y, and the derivative of e to the y will be simply e to the y dy dx. But this exponential function that we have here is not on a base e. So we're going to do some algebraic maneuvers to turn this base b into an exponential base e. So b to the y equals x. All right. I'm going to use this property right here. So I'm going to write this as e to the ln of b to the y equals to x. And again, that happens because if we cancel e to the ln, don't we get back to b to the y? So we're getting to that part. All right? And that's from the second property that we listed before. All right? Okay. So, well, we don't want to cancel. Actually, well, we use those to cancel exponentials with logarithms, but this time we're going to use the property backwards. We're going to put those e and ln back in. So, let me go back. We also have another property of logarithms that we want to recall. So, number 3, whenever we have ln of a to the n, that's n ln of a. I remember the smackdown basketball rule we discussed before. So in this case, the exponent becomes a coefficient. So what's going to happen here? So this y will become a coefficient. So this will be e to the y times ln of b equals to x. But in this case, well, this has the look of an exponential function. Okay, this ln of b is just a constant multiple, like e to the 5x, e to the 9x, you know. However, we always write the numerical coefficient first and then the variable, which is what I'm going to do. So e to the ln of b times y equals x. And we're ready to take the derivative of this function implicitly. All right, again, okay. Quick exercise. What's the derivative of e to the 5x?
5e to the 5x.
5e to the 5x. Essentially, by mini chain rule, okay, the derivative of the exponential is itself, but times the derivative of what we have in the exponent. All right? So we're going to use the same idea here. The derivative of the exponential is itself times the derivative of the exponential, the derivative of ln b. Y is simply ln of b. That'll be the multiple constant, but in this case, because we are differentiating with respect to y, we need to multiply by dy dx, and the derivative of x is just 1. Alright, so let's see about it. Well, so number 1, we may go back to, okay, we cannot cancel this yet. I'm going to go back to reverse the order of the product here, e to the y ln of b. Alright, because again, I'm going to cancel this e to the e and ln back again, but we cannot cancel e and ln while we have some coefficient in the form. It has to be clean e to the clean ln. So what I'm going to do is basketball rule here equals the 1. So this will be e to the ln of b to the y, and only then we can cancel e to the ln again. So we did to do some work and then we undo to get back to the original terms. That's essentially what we're doing. That's a dy dx equals to 1. Cancel this, that's b to the y. That's a b to the y or dy dx equals to 1. Alright, so we want a derivative, so that's dy dx. I forgot the coefficient ln of b over here. ln of b, ln of b, ln of b. I'm going to divide out ln of b, b to the y, that's 1 over ln of b, b to the y. But again, in the same way that we wanted to get a derivative for arc sine, I'm getting as a final result a function that depends on y. So we need to take this back to terms of x. What is this b to the y? Remember, this is x. So this is dy dx equals 1 over ln of b times x. Alright, and that's the derivative of a general logarithmic function. What if, the question is, what if base is e, which is the usual natural exponential? Well, so in this case, dy dx equals 1 over ln of e. What's ln of e? Don't they reduce to 1? So what's 1 times x? Isn't that just 1 over x? So that's how we get the derivative of ln of x. The derivative of ln of x is simply 1 over x. If you have taken calculus before, well, you knew this formula before, perhaps, right? And whether you took this class before or you took calculus in high school, so you have seen this formula. Where is this formula coming from? You may not have seen it before. So it's a derivation that again puts together some properties of exponentials and logarithms together with some implicit differentiation and some additional pieces of information.
Do we need to know how to manually?
No. In practice, all you need to know is the formulas, which I also have them here typed. For a more general composite function, the derivative of a logarithmic function base b is 1 over ln of b times u, and well, times whatever chain rule we need to do. And the derivative of ln of u is simply 1 of u times the du dx, which in general, if we didn't have a u, that's the formula that you know already, maybe. ln of x, the derivative of ln of x is simply 1 over x, because in this case it's just simply x. It's not a composite u that we should need to differentiate via the chain rule. Alright, let's see if we have time. Yes, we have time for at least one exercise. So let's find the derivative of ln of x cubed plus 1. So to differentiate ln of x cubed plus 1, let's use this formula right here. It's going to be short. So that's the derivative. Oh, come on. Yeah, that's the derivative. So that's simply y prime equals 1 over the quantity u. That u is a quantity inside of the parentheses, which in this case is the argument of the logarithmic function, and in this case it's x cubed plus 1 times the derivative with respect x of that argument x cubed plus 1. And what's the derivative of x cubed plus 1? 3x squared. And let's just put this into one single. In practice, this is what you need to know, the formulas and how to use them. You don't need to know these derivations.